So there's two beautiful ideas left to talk about. And both of them you can think of in sort of two different flavors, two different ways. One way to think about it is we're going to generalize Green's theorem in two different ways. But the other way is just to say it has the flavor of the fundamental theorem of calculus, which is to say I want to relate something on the interior to something on the boundary. So the first thing we're going to talk about is Stokes' theorem. So let's start by recalling Green's theorem. Now Green's theorem says suppose you have a region in the plane and there's a boundary. And the boundary has been oriented. So it's not just any boundary, it's an oriented boundary. So if we were to sort of sketch, so what you have is you have some region here in the plane and you orient in a fashion so that when you traverse the curve, your region here is on your left-hand side. Now it's good to remember that sort of philosophy on your left-hand side because if you have holes, then you have to make sure you get the directions right. But also because this is going to generalize when we get up to higher dimensions. Now, the way that we usually state Green's theorem is to say that if I want to know what's happening on the integral on the boundary of the curve of m dx plus n dy, well, that's equal to the integral over the interior of the region of n sub x minus m sub y dA. So that's the way we usually state it. Excuse me. But we saw that there's another way to write this. Namely that the integral here, this is the integral of f dot t ds. And we saw that this particular thing, n sub x minus n sub y, actually shows up in the curl. So when we talked about the curl, that was the third entry. So if you take the curl of mn and something else, call it 0, and just grab the third entry, which is what the dot k does, then lo and behold, that's the right part. Now in essence, what you should be thinking is like, oh, this is almost like f. Close, it's just you add on a third component of 0. So it looks like the integral of f dot t becomes the curl of f dot k. One's a one-dimensional integral, one's a two-dimensional integral. Now Stokes' theorem says, yeah, that's what happens. So what is Stokes' theorem? Stokes' theorem says, now let's take this whole setting, but we're going to move it up into the third dimension. So you have some region, a surface, if you will. So first off, we have a boundary. So this will be our boundary of our surface S. But the surface itself doesn't have to be flat. When we talk about Green's theorem, we're in the xy plane. The plane is flat. The surface could, go down. So here I have this surface. This is my surface S attached to the boundary of S. So it's the surface with boundary. This is one of the hallmarks of Stokes' theorem. You're dealing with the surface with boundary. And what it says is I really have two things I can look at. I can look at the integral on the surface, or I can look at the integral on the boundary. It's a terrible shading job I just did. All right. Now, particularly, if I integrate on the boundary of f dot t, so a one-dimensional integral, that's the same thing as integrating over the whole surface of curl of f dot n. Two-dimensional integral. So I can relate a one-dimensional integral to a two-dimensional integral. Again, think in terms of fundamental theorem of calculus. If I want to know what's happening on the interior, I can check to see what's happening on the boundary. Now there's one important thing, which is you have to decide on orientation. What's the right way to orient? And so we go back to what was happening with Green's theorem. Green's theorem, we said, okay, we want to walk on the curve. So one of the things we can do is we can imagine standing right next to the edge. So I come over here. Here I am, standing right next to the edge. And then I just have to say, which way should I walk if I want to keep the interior to my left-hand side? Or somebody pointed out to me, so you're doing right-hand rule? Yes, that's what we're doing. It's right-hand rule. So that was the orientation for Green's theorem. Now we have two things to orient. And we just have to make them consistent. So the two things to orient are the boundary and the surface. So boundary, that makes sense when we talk about orientation of boundary because there's two directions we can go on a curve. You can go forwards or backwards. But now, what do we mean when we talk about orienting a surface? Well, when we talk about orienting a surface, what we're talking about here is talking about saying which way is the top side. So surfaces usually come with two sides. Now, not all surfaces do. There are some surfaces which can't be oriented. The most famous example is called the Mobius strip. If you've ever taken a strip of paper and given it a half twist and then taped the two ends together, you'll see all of a sudden you've gone from having two sides to one side. You can't orient it. So a surface with two sides can be oriented, essentially saying which way is the top. So you can imagine that we come to the surface here and we stand on the surface and saying we're going to stand on the top side. So here we are standing on the top side. And the question is, well, which way should we walk? Well, if we want to walk so that we keep the interior to our left-hand side, then in this case, this is the way that we're going to walk along the boundary. So that's the orientation for the boundary, but that assumes, of course, that we've said the surface is oriented, so that's the top side. So it's almost like we're upside down to convention. And if you look at this for a second, you might say, isn't just Green's theorem a special case of Stokes' theorem? The answer is, you're right. It is. So do I need to know Green's theorem? Well, it's nice to know Green's theorem. It's an easier case. But in essence, you can always just rederive it. Now, what do we do? In essence, what we want to do is we want to find an answer to something. Now, what is it we're finding the answer for? If we come back and stare at this equation here of what is curl of f dot n, one way we can interpret this is the following. This is almost like the flux. In particular, it's the flux of curl of f. So there's something we want to compute. There's some sort of flow that arises from the curl of a function. And we want to compute that. That's one way to interpret it. There's other ways to interpret it too. But we're trying to find a value of something. And this says you have two options. So how do you go about it? Now, you might say, I notice you used the word 3 and not 2, but well, let's talk about them. Well, one way is you can say, look, I can just integrate the actual two-dimensional integral. So that's an option. That's finding the surface integral. Now, what's wrong with finding the surface integral? Well, surface integrals can be tricky because surfaces might be messy. We've already talked about surfaces of the form z equals f of xy, but not all surfaces can be written like that. So you can imagine that doing a surface integral for some surfaces, this would be pretty challenging. We may not want to do that. Now, we could just say, let's integrate on the boundary. Okay, well, that's an option. And the nice thing is, all right, the boundary tends to be pretty simple. However, we're dealing with the function f. Now, the nice thing about the curl of f is when you take derivatives, oftentimes things simplify. So when I'm working with the original function, I may not have simplified yet. So that's a challenge. So the third thing is to say, well, why don't we change what we do? And in particular, why don't we change the surface we're working with? Now, you might say, doesn't that change the problem? And the answer is no. Because what's happening? What's happening is the following. So here's an example. I have my surface here. It's a part of a sphere, but I've cut off. So it's more or less, it's the bottom like 2/3 of a sphere. And what do I have? Well, I have a boundary. So here's my bounding curve. And now what I look and say, well, look, if I want to know what's happening on the surface, I really only have to look at what's happening on the boundary. All right. So then the next logical step is, what if I had a different surface? So what if I came instead, and instead of thinking this as a curve in space, I'll throw a surface in. But not just any surface. I'm going to pick my surface. I'm going to make it nice and flat. And now I say, all right, well, what does that do? Well, if this is a new surface, we'll call this our surface U. The key here is that they both have the same boundary. So what does that say? It says if I integrate on my original surface of the curl of f, which is del cross f dot n, Well, lo and behold, that by Stokes theorem is equal to the integral on the boundary, which is our curve, f dot t. But this curve doesn't depend on the surface. So as long as I have the same boundary, it's also equal to the integral over our new surface of our curl of f dot n. So the point here is I can pick a better surface. So if you don't like the surface they gave you, pick a better surface. Now, that won't always work, but it works surprisingly often. Surprisingly often, actually. So that's a good strategy to have in mind. All right. Well, oh, there seems to be a question. No.
What does T stand for in that?
T?
Yes.
Tangent vector.
Okay.
F dot t. It's for line integrals.
One more question about that. K.
Sure. Another question about k.
Yeah. What does the K signify there?
K. All right. So let's just recall T, tangent vector. Make notes here. And K is one of our basic vectors. This is the vector 0, 0, 1. So if you think about it, suppose what's happening. Suppose here I'm in three-dimensional space and I'm in the xy plane. So I have here, maybe here's something in the xy plane. Well, what's perpendicular to the xy plane? The z direction is. All right, now, but remember, there's two ways. I can go straight up, or I can go straight down. So, the two vectors which are perpendicular to the xy plane are the vectors 0, 0, something, or 0, 0, negative something. But we want unit vectors, so it becomes either 0, 0, 1, or 0, 0, negative 1. And so, what happened is we made a choice and said, we're going to have 0, 0, 1 be the thing which is perpendicular to the xy plane. In other words, we've oriented the xy plane in three-dimensional space. So this is just saying, aha, lo and behold, what we think is the top side of the xy plane is the top side of the xy plane.
And is that the equivalent of n in the second, in Stokes theorem there?
Yeah, it is the equivalent of n, because it's perpendicular. I'm perpendicular to my region in the xy plane. So here, yeah, this n and that k serve the same purpose. That is true. Also, you can see they match up nicely. The curl of f dot t. So, all right. Well, any more questions? Okay. Well, time for some examples. So, let's let G be the surface z equals x squared plus y squared, where z is less than or equal to 1. And we want to find the integral on the boundary of the surface G of y, x, yz dot t ds, where the boundary of G is oriented so that it is counterclockwise when we're looking from above. All right, well, we should probably draw this. Do we know what z equals x squared plus y squared looks like? It's what? It's a bowl. Yeah, it's a bowl. So, and I'm only going to go up to z equals 1. So at z equals 1, it's sort of the top rim, and then I'm coming down. All right. So there's my surface. Of course, we should shade this a little bit. All right. So, all right. So there's my surface. Now, in the problems, we have to give an orientation. So we either have to tell you how does the curve get oriented, or how does the surface get oriented. But we don't have to tell you both, because once we know how one thing is oriented, we'll figure out how the other needs to be oriented to be consistent. Now, it says here that it's counterclockwise when viewed from above. Now, if you think about when viewed from above, the positive x is coming in that direction, positive y comes in that direction. So in the xy plane, counterclockwise is going in that way, which means that from here, that's how we are traversing. So that's the direction. Now, Stokes theorem says we can do two integrals and we're going to get the same result. So let's actually verify it. Let's actually do both of these. In fact, we have three ways to do this. So let's do all three of them. And maybe we'll have time for the next question. Ah, come on. How hard could this be? We'll find out. Okay, so let's talk about it. So the first option is let's actually do what's asked. Not even use the new ideas. So in other words, we're going to find this curve. Okay, so let's talk about what this curve is. So again, I'm just looking at the boundary of this curve. What's the boundary look like? It's a circle. It's a circle. It's a circle. In fact, we know a little bit more because we're at z equals 1. So it's x squared plus y squared equals 1, which means it's a unit circle. So that's a very easy thing to parameterize. Now, on the unit circle, we're always at height 1 because z equals 1. And when you go in the counterclockwise direction, the easy parameterization, which is the one we'll use, cosine t for x, sine t for y, where t goes between 0 and 2 pi. So, according to this, we can have the following. So this integral here, you can write in the following way. So that is y dx minus x dy plus y z dz. So whenever you see a dot TDS, it's like the first thing dx, second thing dy, third thing dz. So that's our integral that we're going to do. And we're doing this on the boundary. So we just go through and say, well, what is y? Y is sine t dx, negative sine, okay, minus x, which is cosine t, dy is cosine t, okay, and y is sine t, z is 1, and dz is 0. So we're going to integrate that, dt, from 0 up to 2 pi.
Oh, so where did you get that first line there, the y dx minus x dy?
Right here. It tells us that's the integral, y minus x, y, z. So y dx minus x dy, y, z, dz.
Oh, all right.
All right. Now, this looks like it might not be a fun integral, but I don't think it's going to be so bad. What do you see? Yeah, negative sine squared minus cosine squared, negative 1. So this is equal to the integral 0 to 2 pi of minus 1. Well, that's an easy integral. That's minus t from 0 to 2 pi, which is minus 2 pi. All right. Good. Good. All right, well, one down.
Wait,
What? Yes?
shouldn't that be minus 1 plus sine t?
Where?
Times 0.
Yeah. That 0 is very useful. Whenever you can, get 0 involved. It's like a power cleaner. All right. So that's option number 1. Let's do option number 2. Let's do it using Stokes Theorem. Okay, so Stokes Theorem says what? Well, this is going to be equal to the integral over our whole surface of the curl of this vector valued function. So we have to compute that. We'll do that in a second. And then do it dsa. So let's do our curl. So we're going to take I, j, k, partial x, partial y, partial z, y minus x, y, z. And we start going through here. I, partial y of y, z. Well, that'll be z in the I direction. J, partial z of y is 0. K, partial x of minus x is minus 1 times k. Go in the other direction. K, partial y of y, but we have to subtract, so that's another minus k. J, partial x of y, z, well, there's nothing there, that's 0. And partial z of minus x is 0. So we end up with z, 0, negative 2. All right, so there's our curl. So now, what are we doing? whoops, I forgot my dot n. I'm sorry. There's a dot n there. So we're going to integrate over our surface G of z0 negative 2 dot n dsa. So now we're finding flux through a surface. We know how to find flux through a surface. This is equal to the integral over our region R of, well, I'll write the formula, minus m fx minus n fy plus p dA. Well, that is true as long as what? Well, the question is, do we have upward pointing normals? We haven't talked about the surface yet. Which way do the normals point? We should figure that out. So in other words, which side is up? So I want to walk along it so that I want always to have my region to the left. Well, so can you see which side is up? The inside is up, yeah. So the inside is up. Now, you can imagine that if you're a person standing on the inside, so here's a person standing on the inside, and they walk along next to the boundary, the surface will be on your left-hand side. Okay, so that means we did get the right formula, because orientation, if it had been on the outside, it's been pointing downwards, we'd have to put a minus sign. Okay, so let's go through this. This is the integral over our region of minus m. So that's minus z times f sub x. Well, f sub x is 2x. Then minus n, which is 0, times f sub y, which is 2y, plus p, which is negative 2, dA. Now, parts of this integral are easy to compute. For example, 0 times 2y is very easy. That's 0. Now, we're not quite done with this minus z yet. So that's the integral over our region. You have to put everything minus x squared plus y squared times 2x. Okay, good. Plus negative 2 dA. Now, we should talk about the region. What is our region? Well, can you see it? It'd be a circle. It would be, essentially, you'd think about what's the shadow being cast here in the xy plane. It's a circle, and it's a circle of radius 1. All right, one of these two pieces is now easy to integrate, and the other one is also easy to integrate. So which one is easy? Let's start with this one. What's that going to become? And why? Without doing any integration.
Negative 2 cosine t.
Oh, you're doing integration. Don't do any integration. 0. That was sort of the hint. You can't do anything, right? So it should be 0. Now you're probably like, why? And the answer is because. Oh, wait, no, it's not because. Well, there's a reason for it. Okay, here's the reason. Think about the picture. This is my region R. It's a unit circle. If I have a little piece over here, and I flip it over here, what happens to the value? It's the different x values is a different sign. When I add the two pieces together on the different sides, they cancel out. So this is 0 by symmetry. I know that's someone. I know you really want to integrate. I promise you, if you integrate, it turns out to be 0. It's not very exciting. All right. So that leaves us with this other integral, which I say is easy, but that's because you can pull out a negative 2, and then you're integrating over your region dA. So that's the area of A. Well, how much area is there in a unit circle? There's pi r squared, radius 1. So you end up with negative 2 pi. And you see, it's the same. Okay, that's good. It's good we got the same. Now at this point you're probably thinking, this is a terrible method, because that did not take us very long to do the actual line integral, and this seems to take a lot longer. But remember, there's one more thing we can do. There's a third option. What's a better surface for us to work with? The disk. So let's replace this surface by a disk. So here's my new surface. The same orientation on the boundary. So here's option number 3. We're going to integrate, and let's call this new surface h. So we can say, look, this is equal to the integral over h of the curl, which we still have to do the curl. Okay, so that's z0 negative 2 dot n. What's the normal vector? 0, 0, 1. See, because it's a flat disk, the normal vector doesn't vary. It's always the same thing, 0, 0, 1. dsa. Which means this is the integral over the disk of negative 2 dsa. We'll pull out the negative 2, and you're integrating 1 dsa. Well, what is it you're computing when you integrate 1 dsa? It's the area. It's the surface area. Well, how much area is there in this disk? Pi. So negative 2 pi. So if you switch to a better surface, it often becomes an easier thing. We can save ourselves a lot of work. Okay, cool. So now we know we've done 1. Oh, we still have time left. Good. I only have 4 more examples. Okay. We probably won't do all variations in the remaining problems. So let's do this one. Let G be the surface. 1 plus z squared is x squared plus y squared, where z goes from negative 1 to 2, and n points away from the z-axis. Find the integral on the boundary of this surface of yz, comma, 3x plus z squared minus y cubed, comma, cosine of x squared plus sine of y squared, dot t. All right. Let's talk about this problem. So this surface, do you know what that looks like? Do you recognize it? It's one we haven't talked about much. It's a hyperboloid. And what is that? Well, it'll look like the following. Here is at z equals 2. It'll be a circle. So if you fix z, you'll see a circle. At z equals negative 1, it's another circle, but it's a smaller circle. And then you have coming down and out. So that is our surface. All right. Cool. So now we know what our surface is. And now we can talk about our boundary. Well, what's our boundary? Our boundary is actually 2 parts. We have a boundary up here and a boundary down there. So there's a circle at the top and a circle at the bottom. Now let's talk about our orientation. Our surface, we've specified how the normals point. So the normals point, the normals give us the top side of the surface. We're told it's pointing away from the z-axis, which means that as far as the surface is concerned, that's the way up is. So we're sort of standing on the outside of the surface. Now we have to think about how do we treat the boundary. What's the right orientation? So, what is the right orientation? For up here, which way should we rotate? Well, it's definitely one of the two. It's definitely either clockwise or counterclockwise, because there's no third option. You know, if you go counterclockwise, you're back to where you started. So, if you were to go in this direction, walking along, well, what would happen? So you're standing, and as you walk, you'd see that you'd have it to the left-hand side. So that's the right direction, right orientation. And this turns out it's clockwise. All right, on the top. How about downstairs? So will that also be clockwise? No. No, now you got to go in the opposite way. So it's counterclockwise. You got to, well, we've seen this kind of thing before, where we had like a holy thing in the Green's theorem. Okay. So, all right. Now, looking at this integral, it strikes me as being unpleasant, because I see this cosine of x squared and this sine of y squared. That does not look fun to work with. It actually turns out that it's not terrible. But I want to do this using our tools. And in particular, my favorite tool is, let's change the surface. So suppose we didn't want this surface. Well, what surface can we replace it with?
Replace it with 2 disks.
Yes, we can replace it with 2 disks. So we can now say, lo and behold, we have a surface up here that'll fill in that boundary. Another way to think about how to get your surface is just say, here's your boundary. What's the nicest way to fill it in? Now, in our case, the nicest way to fill it in is if I have 2 circles in space, just fill it in and with 2 disks, so that the 2 disks form the region. They form my surface. All right. Now, that forms the surface, yes. One of the things you can do, and since based on our time, I think this might be our last example today, and which is a shame. There's some really good ones here. Don't worry, we'll get a lot more time to do it later in the week. Is I like to think about what happens as you deform things. And so let me sort of give an example here. This is a cup, and it's designed to be easy to transport. And the way you do that is you just sort of collapse it, and it collapses down. So what I like to think of happening here is, intuition-wise, is I like to think of deforming a surface. So I can think of, here I have a surface that's kind of like an upside-down bowl, and what I'm going to do is I'm just going to deform it until I collapse it down to something I like. So now I look like something. I still have the same boundary, but I'm filling in my disk as the surface. So why do I bring this up? Well, one of the ways to figure out what's happening is to sort of say, okay, let's deform the surface and see what goes on. So if you know the orientation for the surface, you can follow the orientation down until you'll get down to your new surface, and that orientation has to match. So in our case here, we can actually think of deforming our surface sort of through a series of stages, like you're deflating a balloon. So I can start to pull in my surface, putting it on some sort of extreme weight loss, if you will, and till eventually I've gone almost to the point where it's a point, and now I just start pulling them apart. So I still have my orientation for my surface, and now I keep separating, and here I'll see that I'll have my arrows pointing downstairs. After I separate, I'll have my arrows pointing up until I deform it all the way down, and I'll see that at the end I'll have orientation down on the top part, orientation up for the bottom part. So there's this idea of deformation that can go on, and I like this idea. It helps me sort of follow through and see what's happening. If I have a hard time visualizing it right away, I think about deform it slowly and see where it goes. So let's use this as our new G. So we're going to just call it new G. Well, how about we'll call it H? Well, no, G is still that surface, but we're going to use H. Use H instead. Okay, and here is H. So H is the union of the 2 disks. All right, well, let's do the work. So the first thing to do is you got to compute the curl. So if we're computing the curl, I, J, K, partial x, partial y, partial z, yz, 3x plus z squared minus y cubed, and cosine of x squared plus sine of y squared. Now, let's be smart. Let's look ahead. What's the normal vector down on this bottom disk going to end up being? 0, 0, 1. pointing straight up. What's this normal vector going to be on the top disk? 0, 0, negative 1. Now, stare at this for a second and let's ask the question, I'm going to take the curl of this thing and dot it with these vectors. Which entries or entry do I care about? I want to care about that last one. So, here we go. Mathematical, we have stuff, more stuff, and then we have the third entry, which we care about. All right. So what's the third entry going to be? Well, that's the k. So it'll be k partial x of 3x plus z squared minus y cubed. Well, 3. And then we're going to have minus partial y of, this is a z, it looks like a 7, y times z. Well, that's going to be minus z. All right. So there's our curl. Well, at least as much of the curl as we need. All right. So here we go. We're going to see that this is the integral. Let's probably split this up into two cases. We'll call this h bottom and h top. Okay, so this is the integral h top of our stuff, more stuff, 3 minus z dot 0, 0, negative 1 dsa. And we're going to add to that the integral on h the bottom. Again, something, 3 minus z dot 0, 0, 1.
Should that be 3 minus y?
Should it be 3 minus y? No, because it's k partial y of yz. So that'd be z. In fact, we'd like it to be z. It's to our advantage. Let's talk about what happens on the top. Now at the top, that's at z equals 2. You'll notice it's always z equals 2 on the top. So I can replace 3 minus z by 5. Because z is always 2 on this surface. I have a fixed height. On the bottom, I also have a fixed height. That's at z equals negative 1. So 3 minus z becomes 4. Oh, you're right. I can't subtract. 3 minus z is 1. Okay. There we go. So it's 1. All right. But 3 minus 1 is 4. At least I got that one right. That's a good sign. So if you work this out, what do you get? Well, up top you're going to get something times 0 plus something times 0 plus 1 times negative 1. That's negative 1. So that's minus 1 integral on the top of dsa. We'll work on that in a second. Downstairs, something times 0, something else times 0, plus 1 times 4, which is 4. So plus 4 times whatever it is on the bottom. But now, we're reduced to surface areas. But these aren't just surface areas, these are disk. So how much area is there? Let's start with, say, the top one. Well, on the top one, that's at z equals 2. X squared plus y squared would be equal to 5. So it's a disk of radius square root of 5. How much area is there? 5 pi. Square root of 5 squared is 5. So this becomes negative 1 times 5 pi. Plus 4. Now we go to the bottom disk. So that's at z equals negative 1. So you get 1 plus negative 1 squared, which is 2. Circle where x squared plus y squared equals 2. Our radius is root 2. So the area is 2 pi. Square root of 2 squared times pi. Minus 5 pi plus a pi gives us a final answer of 3 pi. And we're done. All right. So I think that's not so bad. In fact, that one wasn't so bad, but you have time for another problem. Okay, let's see.
So, how did the 1 plus z squared equals x squared plus y squared tie into this? Where did we use that?
It's our surface to start with. It's right there.
All right.
But we changed it, because we often change our surface. All right. Let C be the curve corresponding to the intersection of x squared plus y squared equals 1 and z equals y squared minus x squared, oriented counterclockwise when viewed from above. find the following. Now, here, there's no surface. It's just a curve. Now, what is this curve? Well, x squared plus y squared equals 1. This is a three-dimensional thing now. If I say x squared plus y squared equals 1 in 3 dimensions, what do you see? You see a cylinder. So there's a cylinder. There's a cylinder. Thank you. So there's a cylinder here. This is their x squared plus y squared equals 1. Now, z equals y squared minus x squared. What is that? Well, that looks something a little bit like the following. It is our saddle. It's also called hyperbolic paraboloid. Now we're taking these two surfaces and we intersect. Now if you take these two surfaces and you intersect, you get the non-mathematical term called the Pringle. Which, in other words, if you've ever eaten like a Pringle chip, that's roughly what it looks like. So, okay, this is not going to be a great picture, but you can imagine you have that. So it's coming down in the x direction, but it's going up in the y direction. Okay, so this is our curve. It does something like that. All right. So here is our curve C. And we want to find the integral along this curve of minus y, comma, arctangent of z, comma, y over 1 plus z squared. Now, looking at this, I feel there's probably a pretty good chance I wrote this problem because there's an arctangent. I'm trying to rub off on the other faculty members, though. So they're starting to like arctangent, too. It's Stockholm Syndrome. You know, if you hang around arctangent long enough, you'll love it. Okay. So here we have this problem. All right. How do we do this? What should we do? Well, the answer is we're going to use our tools. And our tool that we have is Stokes Theorem. Now, one question is, I have this curve in space. Does Stokes Theorem apply if all I have is a curve? What's the answer? And while you think about that, I will not. We already told how it was oriented, so it's oriented counterclockwise. So, does Stokes' theorem still apply if all you have is a curve?
Yes.
Well, kind of. Well, what does Stokes' theorem says? Stokes' theorem says if you have a curve that's a boundary of a surface, then you can transform an integral on the curve to an integral on the surface. So we don't have a surface yet, so we can't quite apply it, but what do we need to do? Make a surface. So if you don't have one, you make one. Well, the question is, which surface? Well, here's a nice surface. This surface came from the intersection. So if you think about what's happening here, is that our curve, our surface, we can use that surface there. Oh, that doesn't even show up at all. Okay, imagine that I'd actually chosen a color that shows up. That is our surface. So we're going to use z equals x squared minus y squared, where we have our bounding curve there. All right. Well, unfortunately for us, there's not a consistent normal. So this surface is not flat. This is not a fill in and get a disk type thing. A lot of times we do fill in and we just get a disk, but not always. That's okay. We can still do the work. So we're going to transform this. Let's call our surface here S. So S is our surface. And here, it's a surface where we have the boundary of S is equal to C. And the other thing is we should note that because of the orientation, the Pringle is oriented. It landed in the right way. So the normals are up. Of course, really, they're a little bit slanted depending upon where you're at in your curve. But okay, the normals face up. They're upward-facing normals. That might come in useful in just a moment here. To start with, we need to compute the curl. So del cross F, and let's hope something beautiful happens. I, J, K, minus y, arctan z, y over 1 plus z squared. And I got that wrong. I, j, k, partial x, partial y, partial z. And then we have minus y, arctangent of z, y over 1 plus z squared. There we go. Now I got that right. So we start taking our curl. So what do we get? Well, we get I, partial y, y over 1 plus z squared. So that's 1 over 1 plus z squared times I. J, partial z of minus y. Nothing. Gone. Great. K, partial x of arctangent z. Also gone. Fantastic. Wonderful news. I, partial z of arctangent of z. Oh, well, that's not going to go away. Because, okay, derivative with respect to z of arctangent of z is 1 over 1 plus z squared. But wait a second. We're going in the other direction. Subtract. Nice. Okay, j, partial x of y over 1 plus z squared. There is no x. 0. K, partial y of negative y. Well, that's negative 1, but I'm subtracting it. So subtract negative 1k. Those cancel. So you end up with the curl cross f is k. That's beautiful. It's almost like they wanted that to happen because they did. All right. So when we're integrating, what? Well, we're going to integrate the curl, which is 0, 0, 1 dot n dsa over our surface S. Well, this is, now we can interpret this as a flow. So you have, this is the integral over our region R, which we'll talk about in a second, of minus m, which is 0, times f of x. Well, look, 0 times anything is 0. Minus n times f of y. Well, it's still 0. Plus p. Ooh, that's called 1. dA. So this 1 here, that's your minus m fx minus n fy plus p. So because we're doing a flux. What's R? What's our region? It's a unit circle. How do we know it's a unit circle? Yeah, our original curve came from intersecting with x squared plus y squared equals 1, which means that when you look down the z-axis, you'll see that the curve is on the unit circle. So R, well, okay, so this is the area of the unit circle, also known as pi. All right, well, that one wasn't so bad. So you can do Stokes theorem. You apply the curl, make sure you got the right surface. If you don't have a surface, bring one. 2 more examples, and we'll be done for now. We'll get more practice in a few more sessions. It's good to practice. The more you practice, the better you get. So we have f, 3x minus y, 2z, 4x minus z, and c is the path from 2, 0, 0. Okay, let's draw that. That's on the x-axis. So here I'm at 2 to 0, 3, 0. Okay, on the y-axis at 3 to 0, 0, 2 at 2, and then back. Okay, boom, boom, boom. It's a triangle. All right. Now what do we want to do? Well, we want to find the integral along this curve of f dot t ds. Now, it's not a bad curve, but the problem here is this is going to be work. Because, not work as in its computation of the work, but work, and then we'd have to do 3 integrals, 1 for each side. Ugh. All right, so we don't want to do that. If we don't have to, we don't want to do that. So, what do? We're going to use our new tool, one of our favorite tools. So, the idea is, hey, this curve is the bound of some region. In fact, it bounds a triangle. Now, of course, there's other options, but here, triangle is probably the easiest one to work with. So, let's think what we can say. Well, it's really part of a plane. Now, which plane? All right, so we have this new surface, z equals f of x, y. Well, turns out in general, if I know where I intersect the axes, there's a very clean way to find the plane. So if I know my intersections are A, B, and C, my intersection is at x over A, my formula, x over A plus y over B plus z over C equals 1. And we can check. Why? Well, suppose y and z are 0. You're on the x-axis. Where do you intersect? Well, when x over A equals 1. So at x equals A. Boom, done. I already hit on the y-axis. We'll cover up the x and the A. Y over B equals 1. Y equals B. And where you hit the z-axis, well, where z over c equals 1, which is z equals c. You have 3 points. 3 points make a plane. So that's your equation. So our plane here, that's going to be x over 2 plus y over 3 plus z over 2 equals 1. That's our surface. All right. Now, well, what comes next? We have the following. Stokes Theorem says that this is equal to the integral over our surface, which we'll call this surface G, integral of G, curl of F, shorthand for curl, del cross F, dot N dSA. All right. Now, what comes next? Well, let's compute the curl. That's probably a good thing to do, because we'll need it. So, switching here to finding curl. So we're looking for del cross 3x minus y, comma 2z, comma 4x minus z. So I, j, k, partial x, partial y, partial z, 3x minus y, 2z, 4x minus z. All right. So I, partial y, 4x minus z, nothing. There's no y. J, partial z, 3x minus y, nothing, because there's no z. K, partial x, 2z, nothing. Wow. We're really batting 0 here. Okay, so that was going down to the right. Now down to the left. I, partial z of 2z, well, that'd be 2. Of course, we went down to the left, so that gives us negative 2. And then we have j, partial x of 4x minus z. That'd be 4, but we went down to the right, so minus 4. And then k, partial y of 3x minus y. Well, that's minus y. But we went down. Minus 1, we went down. So plus 1. So negative 2, negative 4, 1. All right. Well, now what? Well, the next thing for us to do is to figure out how to do this integral. All right, let's just double check. You know, it's always good to double check. So, negative 2, yeah, negative 4. Yeah, it looks good. Looks good. We'll assume it's right. All right. So, we have, it's the integral over g of negative 2, negative 4, 1, dot n dSA. Now, at this point, we can do it sort of in 2 different ways. They're not so far off. Now, one thing we could do is we could actually find n. Now, how could we find n? Well, we have the normal vector because we have the plane. So the normal vector is 1/2, 1/3, 1/2. Now, I said the normal vector, really a normal vector. And now we could say, well, is this the right one? What do we need? Well, if we come back here and think about the orientation, we said, okay, what's the right orientation? Well, we should be up. So we should be coming out on the top side. That's what's consistent with our orientation. So that's good. That's the right z value. Now it's not the right n. Now to make n, we can divide by the magnitude of 1/2, 1/3, 1/2. And if we do this, let's, well, we're already halfway there. Might as well finish. So we get 1/2, 1/3, 1/2 divided by square root of 1/4 plus 1/9 plus 1/4. Well, what does that turn out to be? Well, that turns out to be, if you add 4 plus, well, get a common denominator of 36, then you get 9 plus 4 plus 9. So we end up with 1/2, 1/3, 1/2 over, underneath here, you add those up, you get the square root of 22 over 36, which means, well, that's really a square root of 6, so multiply. So this is 1 over square root of 22 times 3, 2, 3. All right, so that's our n. That's our n. So this is the integral over g of -2, -4, 1 dot 1 over square root of 22, 3, 2, 3 dsa. So that would be integral over our surface 1 over square root of 22 times, well, -6 minus 8 plus 3 dsa. And -6 minus 8, that would be minus 14, plus 3 makes minus 11. So we're now up to minus 11 over square root of 22 times the integral over g dsa, which means that this is -11 over square root of 22 times the area of g. All right, so now we're down to saying, well, what's the area? Okay, well, for that, we turn to our old problems and say, okay, suppose I want to find the area of a triangle, the area of this triangle. One thing I can do is I can take this vector and that vector and cross them, and then take the magnitude and then divide by 2. So here, the vector would be -2, 3, 0. And here, it would be -2, 0, 2. So if you cross these two vectors, I, j, k, -2, 0, 2, -2, 3, 0, what would you get? Well, you get 0i minus 6i, comma, then you get -4j, and then minus 0k, so -4. And then you get -6k, and nothing else. It would be 0. So -6, -4, -6. All right. And you should, of course, be paranoid. Dot product, you can check. Plus 12, minus 12, and 0. All right, it works out. It's good. So what's the magnitude? So magnitude of this would be 1/2 magnitude of -6, 4, -4, -6 is, oh, we're running out of space. 1/2 times the square root 36 plus 4 plus 36, which is 1/2 square root of 36 plus 36 is 72, plus 4 more, 76. All right. So that's the area of A. So, putting those two together, we have -11 over square root of 22 times 1/2 times square root of 76. Now, things could be better, and they are. Well, we can simplify. Square root of 76 is not nice. All right, let's see what's going on here. Square root of we added wrong. Okay, that's what's going on. So magnitude, it's 1/2 of square root of 36. We forgot to square it. 16/36. So that's 1/2 square root of 72 plus 16 is 88. So you get minus 11 over square root of 22 times 1/2 square root of 88. Well, square root of 22, square root of 88, that's square root of 4, which is 2, times 1/2 is 1, negative 11. All right. Whew. Now, at this point, you're probably thinking, that seems like too much work. And the answer is yes, because we did it the hard way. We actually literally computed this integral as given, which is what we probably shouldn't do. What should we do? Well, we should have done the following. We should have said, look, this is the integral over g, -2, -4, 1, dot n dsa. This is my m and p. So, according to our rules, this is the integral over our region of minus m, which is -2 f sub x, well, we'll come back in a second, minus n, -4 f sub y plus p dA. Now, a couple of things we have to talk about. What is r? What is f? Well, f is the plane, so you solve for z. So if we do that on the side here, we could say z over 2 is equal to 1 minus x over 2 minus y over 3. So z, that's the z, is 2 minus x minus 2/3 y. So that becomes the region of -2 times -2, sorry, -2 plus 2, minus makes plus. So 2 times f sub x, well, 2 times -1, plus 4 times f sub y, -2/3, plus 1. And now, what do we have? Well, what we have here is we have numbers. We can figure this out. -2 minus 8/3 plus 1. Well, -2 is -6/3. So minus 14/3 plus 1, which is really 3/3. This gives us a grand total of minus 11/3. So this is what? Minus 11/3 times the integral of your region of dA, which is minus 11/3 of the area of R. What's R? We haven't even talked about it yet. Well, R is the area that's in the xy plane if we were to cast our shadow. So it's this triangle. So what can we say about this triangle? Well, intersections here are at 2 and 3. So the area of R is 1/2 base, which is 2, times height, which is 3. 2's cancel, 3's cancel, and we finally end up with an answer, -11. Again, all right, well, we got the same answer twice. It must be true. It must be true. But, all right, so it's possible. It's possible. You can work with the area of the original triangle, or you can, of course, say, aha, once I get to this point, integral of something dot n, we do our old flux computation. Well, which one is right? The answers are both right. You both get the same answer, and you both need to work. But that's all right. Work is not bad. Okay, one more. Let G be the surface, square root of x squared plus y squared minus 2, quantity squared, plus z squared equals 1, and z is less than or equal to 0, with normal vectors pointing downward. Now, what is this? Well, one of the things you can think of, if you didn't see anything else but just saw this equation, whenever you see something like square root of x squared plus y squared, you can really think of this as r. So it's like you have r minus 2 squared plus z squared. So if you had come and drawn a picture in what I'll call the RZ plane, then what you have is r minus 2 plus z squared would say put your center at 2 and now take a radius of 1. Now that's in the RZ plane. But how do you get to the x, y, z space? Well, the answer is when you're really dealing with r, what that means is there's a rotation going on. So you swing this around. So if you do this, you get another point on the opposite side, circle radius 1, and of course things connect, and sort of the way that you might expect. All right. But there's more. We said, look, we don't want the whole torus, we want the half the torus. So we're not really spinning the whole thing, we're going to spin the half of it. So when you spin the half of it, what you end up with here is you end up with something that looks like this. So that's our shape. It's kind of like, well, it's kind of like a bundt cake pan. If you ever have seen a bundt cake. All right, so there's our surface. Now we're also told that our normal vectors point down. So that while we're on our surface, our normal vectors point in a downward direction. Okay, so here's our surface G. And what do we want to find? We want to find the integral along G of something that takes almost a whole page to write down. Wow, cool. All right, well, how are we going to do this? Well, the answer is this is the wrong surface. I mean, it's a beautiful surface, but it's going to be hard for us to work with. Well, what's the right surface? So we should do a couple of things. One thing we should do is we should think about what's the boundary of the surface. And we can work with the boundary of the surface. So whenever you have a del cross something, so in other words, you're taking a curl, it says you work with the surface that's best. In other words, among all the surfaces with the same boundary, which one is easiest? Now, so what is our boundary? Well, one boundary is the inner part here. So what is that? Well, you come to 1 and make a circle. So it's a circle of radius 1. The other part is go to the outer part and you spin around. Where's that? Well, that's at 3. So now, come out here and we have a circle of radius 3. So those are our bounding curves. And what's our best surface? Well, our best surface would be if we just imagine taking our bundt cake pan and pushing up. So in other words, flatten it out. So if you flatten it out, what you get is you get a very simple annulus, which is a fancy way of saying like a flat donut. So it's a region between two circles. So that's our region. Now, what's our normal vector? Our normal vector is going to point straight down. So it's going to be 0, 0, negative 1. That's n. All right, so we have our good surface, and we know it points down. So here we say, look, the surface integral is okay. We don't need to go to the boundary, so we don't need to worry about the orientation of the boundary. We're just going to pick a different surface. So we're going to call this surface H, and then we're going to say that Stokes theorem says that's the same as solving that. Now let's do the curl here. Okay, so this is going to be equal to the integral over H, and we see that what we will end up with, we only care about the third entry. The first two entries don't matter, so we only care about the third one. So when we do the curl, we're going to end up with something, something, and then the third entry. Now what is that? Well, if you remember how you compute curl, I, j, k, partial partial x, partial partial y, partial partial z, m, n, p. So the third entry would be k, partial partial x of n, n sub x, and then the other way, k partial y of m sub y. In other words, this is the stuff from Green's theorem. And you might say, ooh, that's a nice coincidence. Not a coincidence. Not a coincidence. So you come into here, this is your n, and over here is your m, and this, that goes away. We don't care. That's p. So we're going to take our n sub x. Well, what does that turn out to be? You get 2 plus 2x minus y squared and nothing. Cosine z. That's nothing. Okay. Subtract m sub y. So subtract 2x, and 3z is going to go away because that doesn't have a y. Z squared goes away, and minus x squared. All right. So what do we have? Yep. Oh, whoops, sorry. Positive x squared, but it's going to become a minus when we multiply. Okay, dot, our normal, 0, 0, negative 1. Again, we can only get away with this because we know these are going to be 0. If they weren't 0, we'd have to do the work. All right, dsa. Well, this becomes the integral over h, and if we can simplify, first off, notice the 2x's cancel, and we have 2 minus x squared plus y squared, and then all of that is being multiplied by negative. Okay, so put a negative there, dsa. But really, we can say, wait a second, we're in the xy plane. So here, if we're in the xy plane, then when we talk about dsa, we can really say, look, this is really just dA, because it's back to our business as usual. So what's our region? Well, we're going between a circle of radius 1 and a circle of radius 3. That says polar. So we're going to switch to polar. So switching to polar, integral, integral. We go 0 to 2 pi, and then we go from 1 to 3. So all the way around between circles of radius 1 and 3. And now we're going to get the following. This part becomes r squared minus minus, so it's plus r squared, and minus 2. And then your dA, which is your dsa, is r dr d theta. So, well, this is integral 0 to 2 pi d theta, integral 1 to 3 r cubed minus 2r dr. The first integral is 2 pi. The second integral, 1/4 r to the 4th minus r squared, evaluated from 1 to 3. Now, what is that? Well, when you plug that in, you get 81/4 minus 9, subtract 1/4 minus 1. Now 81/4 minus 1/4, that's 80/4, also known as 20, minus 9 plus 1. So that would be 12. We get 20 minus 9 is 11, plus 1 is 12. And remember, there's times the 2 pi. So we end up with 2 pi times 12, also known as 24 pi. And, well, looks good. It's probably right. At least the ideas are good. And that's what we're after, good ideas. All right. Well, we'll definitely need some more practice, and it's coming.